Water treatment facilities like.
I know. That's
Just run in the city.
It's actually really, yeah.
They have a lot
I
of.
mean, to be honest, like,
He's a
really
great.
rushes are amazing.
I'm friends up there.
But right, nice to that means you're always it's fine. So you
I started having this. Oh, yeah. So it's not so. Yeah, I believe you. That's not her, yeah. So I can't. It's more common. Yeah. Oh, yeah. Yeah. Oh, it's not likely one. If we set yourself really nice. So like there'll be like every. Gotta go past the. Yeah. She'll have in this. If you guys do it. Exactly. I had one that I remember. Like, I mean, not mine, like if it was, yeah, as long as it's available. That's it. You know, kind of thing. I love my mom too, like that. It's retired. No, the only thing is, it could take. It'd be helpful even if. So like, it would like, yeah, but it's not. Yeah.
Summer.
Just highly trying to. Well, because that's how. Some things like mounted and then like got into drive my education. And then, yeah, like. Still like. I know you have to use microscope, it's literally just anxiety speaking.
Yes.
Sorry, it's. Noted. But it's so present.
I'll let you know what are they? Just that's fine.
I have any patience.
Copy. Oh, we can't start middle of the road here. That great.
But you can't stop for just.
Oh, yeah.
No. But I don't.
Yeah, honestly, I just don't really. People. And.
Yeah, these have contact. Speaking of people, like this, like all my things.
Yeah.
Like this person.
Yeah. So.
Let's go to the highway. When I use this one, which is like fine. Yeah.
They're good. Yes.
It's yeah, it's a.
Yeah, there's like. Oh, you know, yeah. Well, yeah. Yeah, exactly. But, yeah, I've seen that's. I don't know. Painful to see. It's on. I can't believe it goes there.
Well.
Probably something. Yeah. Yeah.
Not as expensive as.
Usually it's fine, it's not really small.
Yeah, why don't you get rid of it?
Hey, are you able to go to meeting? I think the meet the one for the. I can, I'll email you the link. Right now, okay. Okay, so the meetings will be back.
I think we're almost at the courses. Go ahead. Hello, everybody. Thank you for being here for Kaitlyn's PhD defense. You'll be amazed and astonished at what she did. Kaitlyn grew up mostly in Maine, I understand. Went to college at Oberlin in Ohio. And then after that, worked for a couple of years in Howie Lasker's lab, working in St. John in the Caribbean. And doing a lot of diving and working in coral habitat or reef habitats there. And then she applied for and got an NSF GRF, which is a signal honor, and contacted me and said, hey, I'd like to be your graduate student. So I said, sure, come on. And she did and has been here now. This is the end of her 5th year. So she is finishing, it's in your 5th year, right? Yeah. Yeah, finishing within 5 years of arriving here. As you'll see, she's worked in a lot of different places, including in the Caribbean and up in the San Juan Islands, where she had taken a course as an undergraduate and fell in love with the place, which most people do who go to Friday Harbor Labs. So she is going to give us a talk today about 3 projects that she's done, and take it away.
All right, is my good on the mic? Okay, cool. Well, thanks Bruce for introducing me. Sorry for the delays, I think I'm pretty scared now. So with that, I will get started. So thank you everybody for coming. I'm a little nervous, but it's nice to see everyone. That's many nice faces in the crowd. So my dissertation is titled Impacts of Stress on Marine Community Dynamics, Multi-Scale Insights from Coral Reefs and Rocky Intertidal Zones. I just want to start with clearing the title so you can see this photo, which I think is really cute, of some sea stars and some intertidal habitat. Okay, so for those of you that are not super well acquainted with the field of marine ecology or ecology in general, just a brief introduction is that ecosystems are, well, ecological communities, I might call them ecosystems, bear with me, are groups of organisms that share a habitat and interact with each other in the context of their environment. So these communities this is kind of a visual of what a community dynamic might look like. So you can see every species has at least one arrow pointing to another one, then you have multiple arrows. So this just sort of captures how complicated these systems are. And you can imagine if one link was removed, or if suddenly it gets a lot warmer, this whole structure and function might start to fall apart. So this is a very big deal because the oceans are getting a lot warmer, and this has happened pretty quickly. This is a temperature graph showing just generally heat stress in the ocean over time, over the past 60-ish years. So you can see things are getting warm, bad news for a lot of ecosystems. So in my 3 chapters, a kind of central focus was about the impacts of stress on community function broadly, and I examined that in 3 different chapters. So my first chapter is about community level indicators of climate change over 3 decades, so kind of a long-term big picture look at what's going on in Washington. Chapter 2 is more about species interactions, so focused on kind of a habitat forming, intertidal kelp, and how the interactions that that's involved with change over a gradient of vertical tidal height. And then chapter 3 is my coral chapter. I'll just link it by saying it's about a stressed ecosystem where kind of the dynamics have fallen apart a little bit over time, and how a potentially invasive species can upset much of the community structure out there. So I guess my timer's going to go over. So my first chapter, I'm going to take us to Friday Harbor, Washington, an extremely beautiful place. I think many of you have been there. This is a view from Friday Harbor Lab. So the intertidal zone generally is the area on a shoreline where the animals are covered and seaweeds are covered at high tide and exposed at low tide. So the things at the very top are exposed to air pretty frequently. At the bottom, they're generally not very exposed. So in this photo, for example, this very lowest zone might only be exposed to air 3 or 4 times a year at the very, very bottom. But at the top, it's more like a daily occurrence. So pretty strong gradient of desiccation stress, which is a big deal if you're an ocean animal. You don't really want to look too far out. So you can see this is kind of a more realistic example of what this looks like in practice with my friend Megan for scale. But on the right, we have kind of a less realistic, but a nice vertical representation of what's going on. So you can see that this upper area is dominated by barnacles, and there's more bare space because it's a slightly more stressful place to live. So nobody's really clamoring to fit in there. But down at the bottom, lower on the rock, where things are submerged more of the time, it's a nicer place. And so this area is dominated or structured more by competition for space and predation. So it is truly a gradient, but the patterns are visible enough that we can talk about these in kind of subzones. So in this case, we're going to call this the kind of upward mid zone and the lower mid zone, as defined by this pattern. So for a single species like these barnacles that you can see, the upper limit, so the highest individuals, are living very close to their abiotic stress, like physiological limits. If they're any higher, they get too hot or they dry out, so they won't do very well. The lower limit, so the very lowest barnacles, that's my example species, these guys are limited. They can't go much lower, else they'll get outcompeted or they heat, so they don't do well down there. So generally, we have abiotic stress structuring the upper parts and biotic stress and interactions limiting the lower zone. So what we've seen over time as things are getting warmer is that the upper limits of species vertical ranges are shrinking down towards the water as the top area, because they're very close to their thermal limit. So if this gets just a little bit warmer, it becomes uninhabitable, and so things move down a little. Because the bottom zone is structured more by biotic interactions and not abiotic stress, we're not seeing shifts in the bottom of species distributions. So this figure shows the pattern I just described for several very common kind of important intertidal species. This graph is from kind of the Strait of Juan de Fuca area. It's from a master's thesis, I believe, by Becca Jansen. So she documented trends of decreasing upper limits for many, many species between 1960-ish and 2020-ish. So definitely substantial evidence for this in mid-zone. And again, no changes in the low zone. So this, I think, is a really compelling story that I find very interesting, but it's limited to single species upper and lower limits and doesn't tell us as much about the community composition and what's happening in these different zones on kind of a more complex multi-species level. So I was interested in investigating this, and I worked in Friday Harbor, Washington, very beautiful place. This is Friday Harbor Labs, Beauhart. So San Juan Islands are much warmer and drier and generally more stressful in the intertidal zone compared to the outer coast because of their location in this little inland sea. So the tides on the outer coast of Washington occur a few hours earlier than the San Juan Islands. So by the time low tide hits here, maybe 3 or 4 hours later. So in the summer, when the tides are really low and the San Juan Islands are nice and hot and dry, this results in midday tides that land at around noon. So that's bad for the low tide organisms. So in addition to being more extreme than the outer coast, Friday Harbor is also a more thermally stressful habitat than many places all the way through California. So this is a graph showing the cumulative midday exposure. So you can think of it as kind of like how stressful is it to be in the intertidal at low tide. And Friday Harbor is second only to Seattle, which is also located inland, so a similar pattern there. So this is a great place to study climate change because if we're going to start seeing responses of whole communities to climate change, we're likely to see them here where species are under more stress, likely to occur even farther north than many of these other more southern sites because of tides, low tide. So, still on, okay. So we wanted to know if the long-term changes in community composition that we might be seeing are consistent with predictions about what we think will happen under climate change. So I'll explain these more when I get to my methods, but kind of a brief overview of how we did this was by comparing the mid-zone communities to the lower zone communities to see if we're seeing more dramatic change vertically. And then we also chose a set of different sites that are located on different parts of San Juan Island, where some are warmer and some are cooler. And then finally, after comparing these kind of spatial patterns, we're going to zoom in and look at what individual species are responding and how they're responding. So the reason we can do this long-term community composition comparison is because Bruce and Jane were around in 1992, and they did these first surveys at many sites, and they graciously gave us their old data books with some unintelligible handwriting, but lots of good data. There was a note that said bunch of crabs, bunch of crabs, bunch of crabs. So, you know, we had some typing and some editing to do, but we were able to use that data as a really good baseline to understand how the 2024 years are different. So our methods involve running this long transect line along the entire or a 30-meter section of the kind of representative low zone at every site, and the same thing in the representative mid zone at every site. So this, from here, we use our quadrat to kind of pick random sections, and the idea is to just get a representative idea of what the community is like. So using our quadrat, we go along and we can identify every single organism to the species level. This took a long time, but we did it. And using this, we can estimate how much cover there is of every single type of thing. So this is a 5x5 grid, so each spot represents about 4%, so it makes it easy to count. We identified everything to the species, but for many of our analyses, we ended up kind of lumping to minimize discrepancy between the years. So, first question that we investigated was if the mid-zone communities have changed more than the low zones. I want to make a little note before I show the results. The mid-zone and the low zones in Friday Harbor and elsewhere are made up of pretty different sets of organisms. So in my next slide, I'm not necessarily comparing the mid-zone to the low zone and saying like this is more this or that or anything like that. We're just looking at mid-zone 92 to mid-zone 24, measuring that distance, and the same thing for the low zone. So on this figure, that magnitude of change is represented by these arrows. So if you're not interested in NBS, you can look at the arrows, and if you are interested, each dot represents kind of a measure of what a community is like. So the dots that are closer together are more similar communities, and the ones that are farther apart are less similar communities. So you'll notice that the round points of the mid-zone are clustered because there's species, and the low zones clustered separately. So the main result here is that the mid-zone does seem to be changing, or has changed more dramatically than the low zone over the same amount of time. Okay, so our next question was about regional differences. So we did find evidence that heat stress in vertical space is having an effect. So we used different sites on different sides of the island to figure out if, to kind of double check that there is a temperature signature here. So our sites, I guess, so the location of San Juan Island relative to the Strait of Juan de Fuca makes it so that when the tides come in, this side of the island gets hit with that cold, fresh ocean water. And then this area up here is almost in like the shadow of that. So it's very warm, less wave action, and a little bit, yeah, I guess warmer overall. So I'm calling these regions. These are farther apart than these two. But the point here is that these more cool colored west side sites are experiencing more similar environmental conditions than these two. So again, we're looking at magnitude of change between years and sites. So we did find that the north side warmer sites changed more dramatically than the west side sites, as we predicted. We also see this trend of similar patterns of change. So the arrows for the north sites are kind of moving together, and same with the west and north sites. So evidence of clustering, which is good. Although all sites were different from each other, but the region effect was much stronger. So those last two NMDS plots, sorry for all the beads, I know they're a little bit much, but those last two had mid and low zones combined, which can obscure some of the patterns that we're seeing. So to get at this more specifically, I've separated these. This NMDS only has mid-zone data for all of our sites. And in this case, we're seeing a very strong signal that the north side sites have changed a lot from 1992 to 2024. So the polygons kind of represent like, this is what the whole site was like in 92, this is 2024. So these guys have no overlap, and the arrows are very large. West side sites change less substantially with some overlap, definitely still different, but less dramatically than the north side. So the low zones, kind of interestingly, did not have as clear of a signal of location on the island. So across all of our sites and different locations, we're seeing changes over time. So the polygons have shifted, but there's still some overlap, and there's not as dramatic a difference in arrows. Magnitude change. So regional differences, yes, but they're mostly being driven by patterns in mid-zone. So the last question that I wanted to go over for this chapter is to take a closer look at how the species are responding and what in the mid-zone and the low zone, what specifically is changing. So across the whole island, the major changes that emerged were in these four groups, so algal crusts, barnacles, pecus, and bare space. On both sides of the island, we saw decreases in algal crusts and increases in barnacles, but things start to be different when we get to pecus. So on the north side, we had pretty substantial pecus declines, but actually increased on the west side, so some signal there. Additionally, we had increases in bare space, but on the north side, but no change on the west side. So to me, these four suggest that the north side mid-zone is approaching a temperature that is no longer habitable for many of these species. So the increase in bare space is suggesting that at relatively the same tidal height, just less stuff can live there. It's a worse place to live than it used to be. And this decline in pecus is kind of matches this fact or this explanation because it's generally a pretty heat tolerant species. And this has impacts for the rest of the community because pecus provides a lot of shade, moisture, for other things. So the west side not having this kind of suggests that if we are approaching thermal limits at the north side, we're not quite seeing that on the west side, because it's a cooler place. So patterns of change in the low zone were not as, the signal was not as clear. We didn't have any changes that were consistent across the sites and the different parts of the island. But on the north side, we had increases in pecus in the low zone and increases in barnacles. On the west side, we had decreases in elk and corals. So one thing that I want to highlight, I think it gets lost a little bit in how I worry about my gets lost a little bit in how I had those slides previously, is this pretty substantial decline in fecus in the mid zone. Oh, we're in the mid side. So fecus decline, and it increased by about the same magnitude in the low zone. So this is suggesting that it's not only becoming less livable in the mid zone, but we're actually seeing a response in fecus moving down. So this is different from the graph I showed at the very beginning, because this is not just the upper and lower limits changing, but the actual presence of this species in the different zones as shown, which is pretty interesting. So conclusions, before I start that, this is a photo of the mid and lower zones at Spirit Cove, which is one of our north side sites. So you can kind of see this fecus barnacle difference. So we found, broadly speaking, that patterns of change are consistent with what we would expect in response to climate change and temperatures. We saw more dramatic changes in warmer habitats, so the mid zone and the north side of the island. Yep. Additionally, individual species responses, like we saw with fecus, are suggesting that in the most stressful combination of mid and north, we are starting to see responses from species that will have community level effects. So that's chapter 1. My second chapter. Oh, no, it's okay. That's okay. I was thinking about it. Thing.
Probably didn't expect it. Sorry.
No, that's okay. I'll see Zoom. Okay, so my second chapter is still in the intertidal zone. We're still in Friday Harbor, but we're now focusing, instead of a whole community picture of what's happening on a general scale, we're going to focus on a very specific, important intertidal species. So this is our hero, Ketophilum sessile, favorite little kelp. It's also known as the sea cabbage. So this is a wrinkly little funny kelp that doesn't have a, many kelps have like a little stem. This one just grows out of the ground like a little cabbage. They're very cute. So these guys live from kind of the lower mid zone, just below where fecus would begin or would end. And it kind of goes all the way down into the shallow subtidal where it would overlap with species like Alaria or Caseria. It's an important food source for many species. And also importantly, we just discussed stressful low times. This provides shade and some moisture retention during these really hot days. So I don't know if you can see, it's kind of a dark photo, but I wanted to highlight, we have a bunch of little guys here hiding out under Ketophilum. We've got a little sea star and a handful of limpets. There might be other things I missed, but yeah, a lot of guys live under there. So one thing that I want to introduce that you'll need to know for this chapter, I'm going to skip a lot of nuance. So if you know the kelp life cycle, forgive me. But the kelp life cycle has these two stages where the sporophyte is kind of the visible kelp. If you think of kelp, it's a sporophyte. And then it has this alternate life stage called the gametophyte, which, don't hate me, phycologists, but sort of functions like a seed stage in a plant. So this can last for a long time. It can survive in conditions that aren't super ideal, where the sporophyte might suffer and die. The gametophytes can stay in place. So these are really important for recovery after disturbance, or just generally providing new individuals for the kelp population. So the process of getting new kelp sporophytes from these gametophytes is what I'm going to call recruitment in this paper. So that's just in this chapter. That'll be the process of new kelps appearing in the area. So something that we know about this species in particular, and its recruitment patterns, is that it really likes recruiting to this type of seaweed. These are coral and algae right here. They're a type of calcified red seaweed that retains a lot of moisture and provides some structural complexity in the area. So one reason that this could be happening is that it's a good place for gametophytes to live, might protect them from grazing. So overall, positive effect of corals on kelp recruitment. Something that has a negative effect on kelp recruitment is this grazer right here, the leather chitin Catharina tunicata. So this guy is kind of a specialist on Ketophilum, lives underneath the canopy, is very common, but loves to eat beige Ketophilum. So these little guys get bunched, except, you know, if they grow beyond 4 centimeters, they're kind of safe, but they're definitely at risk of grazing from the little. So ketophyllum density is definitely like strongly controlled by this grazer. So a paper, a study that was done actually at the same site where I worked back in, I guess, the 80s, removed Catharina and found that when you remove them, ketophyllum goes crazy. So we know that there's a really strong effect of Catharina on ketophyllum abundance. So to recap, we have facilitation by correlants, providing support for kelp recruitment, and herbivory by this little guy who's going to come, this little girl. So we've established Catharina has negative effect, correlates are positive, but something I was interested in is what's going on with the microscopic stages, how necessary are they, or how much do they contribute to recruitment? And is there any interaction between the correlants and the grazers' effects? To study this, I set up a field experiment at Pile Point, which is on the kind of southwest side of the island. It's a very beautiful area. Sarah Selke helped me set this up. So before I get into it, I wanted to just show what these plots look like so you can kind of visualize what's happening in the field. So these are my 6 treatments, and I replicated this block 4 more times. So there's 5 total replicates of the whole experiment at the site. So the first one that I want to explain is the control plots. So these provide kind of the baseline against which I'm going to compare my next treatments. So in the control plots, I removed all macroalgae, all invertebrates, anything that was living, but I didn't scrub. So any gametophytes, which are indicated by my black dots on the figure, should remain present. The borders are painted on with copper anti-fouling paint, which is supposedly useful. It is useful in reducing or preventing grazers from crawling over it. They don't like the copper, I guess, so it keeps them. The correlin plots were established in areas where there were correlins already. I couldn't randomly assign these because it's very hard to transport these. But because of this, it's likely that these are multiple species. So we're looking at a multi-species effect. And in general, I was aiming for at least a 20% cover of correlins when possible. And then finally, to look at the effect of gametophytes, I bleached and completely sterilized another pair of plots so that I could compare this to the controls and see how much difference it makes when you have gametophytes versus if you don't. The sterilization was done by, again, removing and scraping everything, and then applying bleach. So this is a bleach soaked towel, and then oven cleaner, and then scrubbing everything. So these were extremely clean plots. So I want to zoom in on these. Nothing there. So, I guess I can't say for sure that there were not gametophytes there, but I think that there are not. Very clean. So this is a diagram of the overall design. We have our grazer present, grazer absent, and then 3 levels of gametophyte treatments. So I had a handful of predictions that I was interested in testing. The first one was that kelp recruitment density will be higher when grazers were excluded compared to when they are present, comparing this column to this column. I found that is the case. So this figure is showing the estimated number of ketophyllum per plot over the different seasons of the experiment. So this was the first full consecutive year, and then a summer 1 year after that is the last point. So what I found was that pretty early on, as soon as winter of the first year, we're starting to see a difference of higher amounts of kelp in the grazer exclusion plots compared to the grazer present plots. So this trend was maintained over time, and by the 2-year point, seems like it had gotten more substantial. Second prediction was that kelp recruitment would occur faster in correlate plots. So the gametophytes, hypothetically, would be able to recruit sooner because they're in this more preferential habitat where they're not as stressed. So the results for this, you might have noticed that my error bars on the mean plot were relatively large. That was because the average recruitment of ketophyllum was low. The individuals per plot, I think the average is less than 1. So to kind of get around that and explain the patterns that I saw without having to sacrifice too much accuracy, was I made this heat map that shows all of the blocks arranged vertically. So 1 is the highest block and 5 is the lowest block. And then the rows are all 6 treatments within each block. So to look at recruitment in correlate plots versus control plots, we can see that the recruitment events, ketophyllum appeared sooner in the correlate plots than in the control plots. And the numbers are a little bit low because many plots didn't get kelp at all, like these 2. The gray ones never had any kelp in them. But generally we saw that the first kelps appeared in correlate plots. And in the control plots, pitch up a little bit later. So this is a full year and this is almost 2 years later. Third prediction was that kelp recruitment will occur later in the sterilized plots because we need to reestablish a community bank before recruitment occurs. So what I found was not exactly what I predicted. I imagined that these would start to show up if the control was 8 months. I thought maybe 12 months, a few extra months. But what I found was that many of them never got kelp at all. So when the kelps did show up, it wasn't much later than in the controls, but only 4 out of my 10 bleached plots had any kelp show up in the first 2.5 years, even 3 years, because I went back and checked the data set here. But many of them never got kelp at all, which was a more extreme effect than I would expect. So the final major thing that I found that was not predicted was this very strong effect of tidal height on kelp recruitment. So I mentioned at the beginning that all of my blocks were established within the Kaitlyn zone. Vertically, they were within a very limited, small area. I didn't think that they were very different, but the very small differences in block height actually were the strongest predictor of if recruitment would occur at all. All of the blocks were solidly within the Kaitlyn zone, so they had clear, big sporophytes above and below them. But recruitment apparently was reduced in the other zones. These are the same time point 2 years after the start. This is in block 1, and this is what block 5. They're different. Again, because I have low averages, I wanted to put up this little heat map that kind of captures the general patterns across grazer treatments and forage, or the grazer treatments, humidified treatments, and block height. So you can see this clear pattern of much lower kelp abundance at the top, higher kelp abundance at the bottom, and higher overall when grazers were excluded. These little asterisks just represent plots that were underwater, not accessible during at least one of my sampling periods, so these are likely underestimates. So in conclusion, what I learned from this chapter was that kelp density was higher in the grazer exclusion areas than when grazers were present. Recruitment was accelerated by corallins. Sterilization delayed or prevented recruitment for at least 2 years, which is a much stronger effect than I expected to see. And importantly, there was very low recruitment success in the upper part of the vertical range. So in my first chapter, I talked about the different controls. And generally, I think of those as kind of distinct zones of different species. But in this case, this species is experiencing kind of like an upper and lower zone effect within its range. So essentially, broader impacts for the whole community if this habitat for species is not able to perform its function in the higher zones. Okay, chapter 3, we're on to the coral reefs. Yeah, so this chapter is kind of we've done community level, and the second chapter was about interactions. This third chapter is more about how whole sets of species respond to a stressor can kind of predict or accelerate or interact with climate change impacts. So coral reefs have been under very high stress for decades from increasing temperatures, diseases, loss of herbivores, overfishing, lots of bad news for the coral reefs. Temperature is a very strong one that is primarily responsible for a lot of the shifts that we're seeing in community composition. So as scleractinian corals decline and other things increase, all of the whole web of dynamics that structures a coral reef has kind of been weakened and in many places kind of fallen apart completely. So this weakened community structure has resulted in kind of a higher vulnerability to disruptive species like invasives or non-invasive species that have been present but may be released from competition or might be entering a more ideal thermal range for them. So one species that is acting like this is this algal crust, Rimacrustid textilis, which is a calcified non-coralline crust found in the Caribbean. It's in the group kind of with basinellid algal crusts, if you're interested. So this crust is kind of bumpy and funny looking, but you can see that this growing edge interacts very aggressively with other stuff. So here's how it's fun. Yeah, that's Rimacrustid. So this species is relatively new to the Caribbean. The first documented report was from 2009, Jamaica. It's likely invasive. We don't know that for sure. So again, this could be an example of release from some constraint or an invasive species. And most importantly, it kills corals which is terrible. So this species has moved pretty quickly throughout the Caribbean over the past decade or so. And it's probably in more places by now, but yeah, extensive spread in a very short amount of time. And this is the impact of Rimacresta on big coral. This is one that you would think of as kind of a massive reef building structural coral. And under prolonged thermal stress, these corals that used to be competitively dominant are slightly less or reduced capacity to resist overgrowth by Rimacresta. So my questions, in the context of this kind of weakened, stressed community, how well are the different organisms able to handle this competitor? What patterns are we seeing of who's going to do well, who's not doing well? And then second, does Rimacresta impact settlement and survival? So kind of the future recovery of any organisms on the reef. Combined, these two questions address multiple life history stages and kind of have broader impacts that I'll talk about at the end. But the adult and juvenile combination is, I think, pretty compelling. So I work in St. John, US Virgin Islands, which is a very beautiful place just east of Puerto Rico, down in the Caribbean. I worked at 5 sites. I won't talk too much about the differences between sites today, but they're all within a relatively close area in a region of St. John that is mostly dominated by octocorals and has relatively low sclerotin cover. I think it's less than 7 or 6% at most sites. So to investigate the patterns of response to Rimacresta, I conducted these competition surveys, again along transects, this time underwater on scuba, where we laid out this transect and proceeded along, scoring every single interaction between Rimacresta and any other organism that it was coming into physical contact with. In the end, this was over 2,000 interactions and more than 90 species for competitors. So for every interaction, we scored what species was interacting, the size of the competitor, and the outcome of the interaction. Possible outcomes include, these are all from kind of, the whole talk is from the perspective of Rimacresta, so a win is Rimacresta win. People. So in the interactions that we scored as win, we saw a clear overgrowth kind of interaction boundary where the growing edge of Rimacresta is visibly sitting on top of the competitor. Kind of looks like a being swallowed whole or something. It's not very good. A Rimacresta loss would be scored when you can see the growing edge of our competitor sitting on top of Rimacresta, so kind of an active overgrowth. Mixed outcomes were cases when there was a win by Rimacresta and a loss within the same colony or the same organism, the same individual. And finally, tie interactions were cases where there was a clear interaction boundary, but nobody was really winning. So you can see there's kind of this squiggly line where they're coming up against each other, but no one's winning. So what we found was that across all of the sites, similar patterns, majority overgrowth by Rimacresta in all places. This ranged from about minimum, we found 70% overgrowth, and the highest was about 80%. So we're looking at a solid majority win by Rimacresta. When we look at taxonomic groups and compare the different types of organisms that we see in a reef, this figure is showing wins by Rimacresta, so tall bars Rimacresta winning. All groups were also overgrown most of the time, except for this zoanthid group, which only had a single species that was a very aggressive competitor, never lost to Rimacresta. But everyone else, especially these scleractinian corals, well, actually, all of the groups lost most of the time. So on a higher resolution level, to take a look at what these competitors were and how they were able to respond, I had 5 consistent winners or species that performed really well against Rimacresta, and very well is relatively speaking because these were still overgrown more than 50% of the time. But we had the zoanthid and octocoral, a kind of fast-growing, more stress-tolerant scleractinian, and 2 species of sponge. The consistent losers against Rimacresta included mostly these big, massive coral species that form coral reefs. So these are the ones that we know and love that are all dying. They also lose to Rimacresta. So the patterns that I found of who was doing well and who was not doing well sort of mirror the predicted trends in changes in reef community composition due to climate change. So the species that are a little bit more stress tolerant and that we're seeing more of, like sponges and octocorals, performed a little bit better against Rimacresta, broadly speaking. So while Rimacresta itself is not necessarily a climate change direct effect, the process of Rimacresta and interacting with all of these species will likely accelerate or kind of reinforce the trends that we're seeing based on temperature and abiotic stressors. So the second part of this is a settlement and recruitment study that we did that I'll just talk about very briefly. But we were interested in knowing if there was a mechanism by which Rimacresta is reducing settlement by other things, or an anti-fouling mechanism. So on the reef, Rimacresta is generally very clean. You might have noticed in those photos there's nothing growing on it. So to see if this is actively inhibiting settlement, we use this octocoral Plexaura mamala and let them settle on both crustosporulins, which are really good for invertebrate recruitment, and on Rimacresta, which is our villain of the story. So these little guys, the white dots, are baby octocorals. What we found was, so this is an electivity index. Generally, what this is showing is a response around 0 indicates kind of a neutral response, no preference or avoidance. Positive values, like in CCA, indicate preference for this area, and negative values, like you see in Rimacresta, indicate an avoidance of that settlement. So octocorals definitely preferred to settle on CCA and avoided Rimacresta, which is consistent with our kind of expectation that there's some mechanism keeping this clean. Conclusions from this chapter. First is that Rimacresta, this potentially invasive evil crust, is outcompeting most reef organisms across many groups, especially these big reef-building corals. But some heat-tolerant species and stress-tolerant species seem to do okay. And if they can't win, they can at least resist overgrowth some of the time. Settlement and survival also seem to be inhibited by Rimacresta, so this is kind of leading to a multi-stage reinforcement of what's going on. So under climate change, like I mentioned, this may not be the ultimate downfall of coral reefs, that's more like temperature, but this can accelerate or kind of reinforce the changes that we would expect to see. Okay. So I'll combine to kind of recap what the chapters were. In my first one, we looked at long-term changes on a whole community level and how those patterns are consistent with what we'd expect due to climate change. Chapter 2 was a smaller scale example of how these kind of sensitive interactions that shape communities respond very strongly to even minor differences in vertical height, so very sensitive to abiotic stress. And finally, chapter 3 was about Rimacresta and how competitive interaction on a weakened ecosystem can really upend the entire community. So combined, each of these 3 chapters kind of contributes to how we understand stress in community systems. They're all very different places and they're different questions and different organisms, but in a sense, they're all very related. I think in the future, as climate change continues to ruin ecosystems and cause problems, studying things on multiple scales, so looking at whole communities, interactions, and single species responses is going to be really useful. Will be necessary, in fact, to kind of understand the broader implications of climate in animal systems. And the good news is I get to keep doing this as a postdoc with Bruce, so I'm excited to keep working on many of these questions, especially the more temporary ones, even that's being fair for me. Okay, still ending on time. So with that, I want to thank all of my committee members. I have 7 because some people couldn't make it, but I want to thank Bruce, my advisor, who let me do essentially whatever I wanted and supported the whole time. Ali Barner, who's been helping me think about this since I was an undergrad. My data film chapter kind of inspired by her dissertation work. Sarah Henkel, who's been on the community the whole time for all 5 years. Thank you for all your help and your great questions during my orals. I really thought about those a lot for a long time. To Megan Detier, who's kind of been one of my science heroes for a very long time. And before now, I've never had an official title for how I know her. So now she's officially my committee member, which I'm very honored to have her on board. She also is the one who did that pedophile study at that site before me. So Megan has been a huge champion of my science for a long time. Lisa Trong, thank you so much for joining and being my PCR on very short notice. I really appreciate it. And Felipe and Kim, who are not here, but they were my committee members previously, they just had conflicts. They couldn't be here. I also want to thank all of my funding sources. The major funding that I have for all of my research came from the NSF JRFP, from student fellowships at Friday Harbor Labs, and from Peace Scout as well. I have so many people for all of my chapters to thank. So chapter 1 took place largely on private property. So I want to thank Michelle Westover and Susan Swindells for letting us work on their beautiful backyards. Morgan Johnson and Keith Constable let me live with them when I had a parrot, which was amazing. So I could do all of this research. Wouldn't have been possible without them. Leanne for dealing with all of my receipts. Sorry, nightmare, your best. Robert Smith helped me with statistics. Megan James and Max Wenzel heard this talk 25 times a few days ago. And then several funding sources, including the Brooks and Suzanne Reagan FHL Fellowship, several FHL fellowships, in fact, for both me and Augie, and then other smaller grants from AMH and IPS. So chapter 2, I think, might be my highest person effort project. So Sarah Selke and Andy Marquez came up and helped me set this whole experiment up. We were out there early morning scraping barnacles and clearing little plots. Also, I want to emphasize, thanks to Suzanne and Brooks Reagan, this was in their backyard, literally like in front of their house. So I would drive up and say, hey, I'm gonna go look at the kelp. I showed up once at midnight on Thanksgiving, and they're like, what are you doing here? But they were very gracious and let me live there for a long time. Tom Mumford and Wilson Freshwater, who got me started on this project 7 years ago, still working on it. Megan Detier for getting me connected to Pilot Point. I guess many things, a lot to thank Megan for. Megan Wenzel and Augie Kolachuk Davis, I think, came with me. If I went 20 times, I think they came with me 18 of those times. So I couldn't have done it without you guys. The best. Millions of other people helped me in the field. I tried to keep a complete list, but if you're not on here, it's not because I didn't mean to put you on. There's just so many people. This was a night in January that I went out 2 nights in a row, and I think I had 6 people in January volunteer to come with me. People I barely knew at like 1 in the morning in the winter. So that was amazing. Wouldn't have been possible without everybody that helped me work on it. In chapter 3, I was lucky enough to kind of be a part of 2 or 3 different lab groups during my time at grad school. This was the Lasper lab at the University of Buffalo. They very kindly adopted me and let me join them on all the Caribbean adventures. So this was a great experience, and I really learned a lot from all of these guys. And these are some of my undergrad students that work on this project. Finally, well, not finally, I have a lot more slides, but there's also a handful of people that I really want to thank. Wouldn't have been possible without all of my Friday Harbor people in different communities. So my friend Lori, she's great. Fed me a lot of dinners while I was working, kayaking in her backyard. Morgan and Keith, like I said, they're really cute. The whole Friday Harbor Labs community, I kind of wish they could all be here at Defend Up There or something, because they've been amazing. I just show up and it's like the best place to work. Everybody's so kind and so helpful. I want to thank my class also from this spring, who were so good and so gracious with me while I was writing and freaking out and teaching full time. It was crazy. Also, Scott Lindell and Allison Leshin and the whole lab at Woods Hole, you guys were awesome. I know it's kind of stressful to have probably a 5th year student who's writing a dissertation show up and join the lab, but these guys were so nice to me and let me stay with them and taught me so much about kelp culturing and let me join their Woods Hole group. These are the people who kept me sane largely while I was writing this, and who also I might have made less sane because they had to listen to this for 13 hours yesterday or something. So everybody on here has heard this talk a lot of times. Everybody's really cute and nice. This is Max, special guest. I think he's in the hallway. I know I said this before, but I really want to thank Augie and Megan, because basically everything I did, they did like 80% of it with me. So really community projects. Megan is really my science consultant, so I call her all the time. Megan, I need help, please talk to me. So she's been amazing. She even flew all the way to New Zealand to hang out with me and help me do field work. So that was very cool of her. And okay, finally, I want to thank my family. or keeping me by the beach all the time and generally being very cute and supporting me in all of my adventures. I think this was my first day of school at some point, so I thought it would be fitting for my last day of school. Okay, thank you.
Questions?
KT, on your third chapter, is there a herbivore that eats Ramacresta, and what's going on with that part of the story?
So, hello, I should have put some photos in here. Ramacresta generally does not seem to have a super active herbivore. I've seen in some places where diadema is still present in super low abundance, but there might be like 1 or 2 diadema in little holes. I have seen grazing marks on the Ramacresta where diadema are present, but their abundance is so low now that I think functionally, even if they can eat it, we don't have enough herbivore density of it.
Do we know what eats it in the Indo-Pacific?
I don't know about the Indo-Pacific. It's also not the exact same species. It's just it's related to species that are there, but it's a different. But I don't know about that.
So we have a question over Zoom by Angelina Zulo. Great presentation. For chapter 1, did you qualify environmental differences between the West and North? And if so, what were they? Water temperatures, air temperatures, etc.
That is a really good question that I knew I was going to get. So I was not able to find high resolution data enough to find differences on the side of the island. So we have at Friday Harbor Labs a great long-term temperature station, but nothing specific as far as the size of the island. So I don't have temperature data. I do have kind of anecdotal reports from fishermen. One specifically that I know who I talked to for a long time about this, he's noticed that the temperatures consistently on his readings at least are 2 degrees warmer in Spiden Channel than they are on the west side near the kind of Salmon Banks area. So I don't have small scale spatial temperature differences, but at least not in like a long-term data format. But yes, it makes sense. I explained everything really well.
Let your questions come out.
Maybe one thing that I'll talk about if I was a little worried about time, but if I have another minute, Megan here asked me to put these figures in, so I put them at the end to share if I have time. So to go back to my chapter 2, the grazer kelp chapter, a caveat that I did not want to get into so that I could end before 1 is that my grazer treatments were somewhat inconsistently maintained. So the copper paint lasts for a decent amount of time, but during kind of, wave action stuff, like the kelps will brush off the paint over time. So since I was driving from here to Friday Harbor every single month, and 1 month it was like an ice storm, winter, there were months that I couldn't maintain my exclusion treatments. But something kind of interesting that happened that I think explains a lot is that the exclusions, I think, were well maintained at the beginning, enough to give certain plots enough of a head start during that time to maintain the differences throughout the experiment. So what I actually found is that in my grazer exclusions, there were more Catharina. So I think this happened because there was enough of a head start that many of the little Pedophyllum could escape that grazing risk size and become established. And so then by the time spring and summer rolled around, the plots that had nice big Pedophyllum canopies attracted more Catharina. So I didn't want to put this in as like grazer exclusion, I have way more grazers without time to explain it, but I did see this trend. That's kind of interesting. I also want to highlight that the grazers, I only mentioned Catharina because that was the only one that seemed to respond to my exclusion treatments. There were no differences in grazer exclusion treatments. The limpets were not different between the treatments over time. There were more limpets in the higher zone. So blocks 1 and 2 had pretty high limpet densities, but otherwise they were relatively lower. And Catharina these error bars are pretty big, but consistent statistically throughout all 5 blocks, but a little bit higher anecdotally. And but Catherine was definitely the more consistent Fraser.
I have a question about this chapter. Just out of curiosity, did you record like how many film recruits were outside of your plots? Because like 1 to 2 seems really, really low in general. Like, is that happening everywhere, or just in your plots?
I only kept track in the plots, but I think having worked in Friday Harbor and now coming back to Oregon and kind of checking out the air title zone, I think it just is that recruitment is a lot lower. So on the bear in the heated film zone, even towards the lower end, any area that is kind of just flat rock tends to be bare space. And so the heated fellow little guys only really recruit to the correlins or lower down. But in most of the zone, they're only able to recruit what I've seen in little cracks and crevices in the rock. So I think it's just a harsher habitat, potentially limiting how many recruits there could be. But yeah, it was very low.
Anything else? Before I ask you to thank Kaitlyn for the talk, we are planning on having a gathering in what is the room number?
3405, that's the big conference room at Courtly on the third
On the
floor.
third floor.
Yeah.
That will start around two-ish. And for the committee, the 3 of us that are here, we're going to room 2414. Otherwise, thank you.
Really faster.